Hi, I'm Péter Vrana from Budapest. My talk is about a family of multipartite entanglement measures. It's based on a preprint that you can find on the archive with a similar title. I'll start with a short summary of the result in the simplest possible terms. We fix a bunch of parameters, a number alpha, which is between 0 and 1, and theta 1 from theta k, which are non-negative numbers summing to 1. And with these parameters, for every pure state vector on k parties, I define the following quantity given by this optimization over various objects like diagonal density matrices on each of the subsystems, and unitaries and real diagonal matrices and upper triangular matrices also on each of the subsystems. So this is where the state enters the formula. And the claim is that this quantity is additive under the tensor product, and at the same time it's an LOCC monotone. So that's the main result. And in the rest of the talk, I will provide some contexts and more details on these quantities and explain a bit how the form can arise. So I'll be talking about probabilistic entanglement transformations, and these will be the kinds of transformations that can be bounded using this entanglement measure, and the so-called asymptotic spectrum of LOCC transformations, which gives a way to systematically study the relevant entanglement measures. In this case, in this problem, then we'll see how this result fits in this picture. So for a probabilistic entanglement transformation, we take a pair of k-parallel states, psi and phi, and we want to transform psi into phi. So we compare them via LOCC, that is local operations, classical communication, which means we imagine that these states are distributed among k parties, and each of them can act on their own subsystem in any way. So any channel can be used to process the state, but between the parties only classical communication is allowed. And the way this becomes probabilistic is that we allow the protocol to abort with a certain probability. So this is how I can draw this, how I can write this down. So when we act with the channel lambda, which is an LOCC channel on the initial state psi, then with probability p, we get the state phi, and with probability 1 minus p, we get some other chunk state. And what we assume is that this chunk state is locally orthogonal to phi, so that it can be distinguished by LOCC perfectly from phi. So without loss of generality, we may think of this as a separable state that's locally orthogonal to phi, and we will not really care about this second part. And the best thing to do in this case is to actually remove this second part from the description completely, and we can do this by allowing LOCC channels to be trace non-increasing. So the local channels in the definition of LOCC will be replaced by completely positive trace non-increasing maps, and classical communication stays the same. So in this picture, square root of p times phi, the vector phi, corresponds to phi with probability p, so to say. So we can just write, instead of this formula, that there exists a trace non-increasing LOCC channel lambda, such that lambda applied to the projection onto psi is p times the projection onto phi. And by linearity, we can just freely move around these coefficients, and what really matters is the ratio of the norms, which gives the success probability. In particular, we will be interested in the asymptotic setting of transforming many copies of the initial state psi into many copies of phi. So suppose we have n copies of psi and want to get r times n copies of phi, and as n goes to infinity, we wish to maximize this rate r. But we combine this with the aforementioned probabilistic setting. If we do this by choosing the norm of psi, or the norm squared of psi to be 2 to the r, and the norm squared of phi to be 1, then that means that as n goes to infinity, the probability of successfully transforming psi into approximately Rn copies of phi decays just to the minus Rn. So this is what's called the converse regime, when the success probability goes to 0. But we want to have a control on how fast this probability goes to 0. So ideally, we would like to get a large rate R with a small rate of decay. So to capture this trade-off between the two quantities, we define E star of R comma psi to phi to be the supremum of the achievable rates R given an error exponent given by little r. So we want to determine or bound this quantity, and the higher the better. For example, this has been studied in the bipartite case, in a special case of entanglement concentration by Hayashi and co-authors. So we have a bipartite pure state, and we fix the target state to be an E-bit. That's what entanglement concentration refers to. And from n copies, we wish to get, or we have to distill approximately E star of R psi to E-bit times n copies of the E-bit, with a probability decaying as 2 to minus Rn. And there's a formula for this optimal rate, which is given by an optimization over Rényi entanglement entropies. So the Rényi entanglement entropy of a bipartite pure state is simply the Rényi entropy of any of its marginals. So we can write it like this. We take the projection onto psi, and take the marginal on the A part, and raise to the alpha power, take the trace logarithm and divide by 1 over 1, so divide by 1 minus alpha. So this these Rényi entanglement entropies enter the formula for this trade-off curve. So how does one find such a trade-off? There are naturally two ways to attack this problem. One of them is to find constructions, that is LOCC protocols transforming psi to phi, or a certain the same with a certain probability, or with many copies, like transforming n copies of phi to r times n copies of phi with success probability roughly 2 to minus r times n. If we do any of these, then what we get are lower bounds on the best achievable rate. So this E star given this error exponent r. The other way is to look for abstractions, which most often come in the form of entanglement monotones, which are quantities that decrease under applications of LOCC channels. And once we find a suitable entanglement monotone, then we need to understand its values on n copies of psi and r times n copies of phi, and then requiring that this quantity does not increase. That puts some constraint on r and give upper bounds on the optimal rate. So in this talk, I was focused on the second approach. And there is actually a systematic way to do this in the setting of probabilistic exact transformations. And this is what the asymptotic spectrum of LOCC transformations is about. So we define the asymptotic spectrum for a given number of parties as a set of functions from vectors in k-pi-table spaces. So you should think of these as unnormalized state vectors, where the norm is not something that we ignore, but something that we use for bookkeeping of the success probabilities. So from these vectors to the non-negative real numbers that satisfy the following axioms. Namely, they should be multiplicative under the tensor product, additive under the direct sum. So this direct sum is can be understood as a superposition of the two state vectors, which are first rotated to be locally orthogonal. They must be normalized. That means they take the value 1 on separable state vectors of unit norm. And they must satisfy this kind of monotonicity property. They must be non-increasing under trace non-increasing LOCC transformations. Whenever we have such a quantity f, and it gives an upper bound on the achievable rates because of the following reason. If suppose we can transform n copies of psi to r times n copies, or r times n plus little n copies, so up to sublinear correction, r times n copies of phi with success probability 2 to the minus r times n. Then if we apply f to this inequality, so using that f is a monotone quantity, and we use the multiplicativity property, then we get an inequality between f evaluated on 2 to the r half, so like the square root of 2 to the r times psi, so on this unnormalized vector, and this value on phi, which involves the rate r. So by taking the logarithm and dividing by the logarithm of f of phi, we get an upper bound on the possible r's. Since E star was defined as the supremum of these achievable r's, we also get an upper bound on them by each of these functions f. So this gives a way to get upper bounds, and as we can see, we didn't even use properties 2 and 3. It's only about properties 1 and 4 that this derivation uses. But the interesting thing is that even with these additional axioms, there's a theorem in our earlier work that this E star, this converse rate, so given a converse error exponent, is actually equal to the infimum over the asymptotic spectrum of these upper bounds. So in other words, these are the only kinds of upper bounds that one ever needs to consider if one is to find the optimal rate given a certain error exponent. So these functions are they form what is called the asymptotic spectrum of LOCC transformations. Again, let's have a look at the bipartite case. In this case, so the bipartite asymptotic spectrum is given by a family of functions parameterized by a single real number between 0 and 1, this alpha, and it's essentially again the Rényi entanglement entropies of parameters between 0 and 1. So up to this exponentiating and the prefactor, we get these functions. So our general characterization gives this formula for the optimal rate given the error exponent. And as we can see, this generalizes Hayashi and Kortha's result. on the internal concentration, because when phi is the EBIT, then all its entanglement entropies are equal to 1. So let's have a look at the points in the asymptotic spectrum. So these functions that satisfy these axioms, what were the known ones before this work? And for charting this this set, it's useful to introduce a function on the asymptotic spectrum given by simply the logarithm of the value of this element of the spectrum on a separable vector, separable unit vector times square root of 2. And one can show that this will always be between 0 and 1. And this will really play the role of the order parameter of the Rényi entropy. So that's why this letter alpha is chosen. So first of all, there's a unique point where alpha equals to 1. So there's only one f whose alpha evaluates to 1, so which evaluates to 1, which evaluates to 2 on the square root of 2 times the separable vector, and that's the norm squared. That is easily seen to satisfy all these axioms. And for each of the subsystems, we can form the marginal Rényi entropies. So these will be Rényi entanglement entropies across certain bipartite cuts. So these are also in the spectrum. And more interestingly, if we take the elements that have alpha equal to 0, then they form what is called the asymptotic spectrum of tensors. And its known elements are a family parameterized by a simplex. So again, we have these parameters theta 1 up to theta k that are non-negative numbers summing to 1. And the value of these elements in the spectrum are given by a certain optimization, which is over the entanglement polytope of this state. And the objective function that we are optimizing is a convex combination of the entropy. So we call that the entanglement polytope. Can be imagined in a way that we take the SLUCC orbit of the state. So we act on psi by all the possible SLUCC transformations and the resulting states. So we take the resulting states and normalize them and collect the marginal spectra. So the spectra of each of the marginals in decreasing order, so that get a polytope. And then for each of these marginals, we can compute the entropy and take a certain convex combination of these entropies, and then take the largest possible value that we can get from the entanglement polytope. And that also gives elements in the asymptotic spectrum of tensors, which is a subset of the asymptotic spectrum of LCC transformations that we care about now. Right, and there's also a nice picture behind this. If we fix now K to be 3, so we have 3 parties, then we can draw a picture of these. So this shape represents the asymptotic spectrum of LCC transformations, which is not a well understood object. So that's why I use this irregular shape. But inside it, there is a point which is the norm squared, and these maps that I wrote down are not disjoint sets of maps, so there are small overlaps. Namely, if we take these exponentiated Rényi entropies, then so these marginal Rényi entropies, they will meet at the point alpha equals 1. So that's where they all meet, but otherwise these are disjoint lines in the asymptotic spectrum. And the other endpoints of these lines are simply the Schmidt ranks across these bipartite cuts, which are also known as the gauge points in the terminology of the asymptotic spectrum of tensors. And these functions that we found earlier interpolate between these gauge points. So one can imagine a tetrahedron with one of the vertices, the norm squared, and the face that's opposite are these interpolating functionals. And these three lines are the marginal Rényi entropies, essentially. So in this talk, I will introduce this family which kind of fills in this tetrahedron. So we get a solid tetrahedron consisting of elements of the asymptotic spectrum. So the question is how to find such an interpolating family. So let me arrange these known points up to logarithms in a small table. So the first row corresponds to the bipartite monotones, which includes the Schmidt rank and the Rényi entropies, entanglement entropies, whereas the first column corresponds to the alpha equals 0 section, so the asymptotic spectrum of tensors, which are in quantum info terms, these are SLOCC monotones, satisfying these additional axioms of additivity and multiplicativity. And the question is what goes here. So this kind of problem might be familiar from IQ tests, when you need to find the pattern and the missing formula. Well, I guess that would be maybe missing shape, but it's all the same. So in order to do that, to fill in this table, we need to look for things that are common in these formulas. And in order to do that, we should recall that these Rényi entropies also have a variational formula given by a supremum over probability distributions of a combination of an entropy, of the entropy of Q, and a kind of distance from P, which is in this case the relative entropy distance. And there's this alpha parameter which governs the relative weights of these two terms. So there's a negative sign here, which means this formula favors Q's that are close to P, and the larger alpha is, the more the formula favors Q's that are close to P. So if we do this replacement, then this is how the quantities look like. So also the Schmidt rank can be written in such a way, so as a supremum, namely we just take the supremum of the entropies of all the distributions that are at a finite distance from the order spectrum in terms of relative entropy, which means nothing else than the support of Q is contained in the support of the spectrum. So this, if we look at these formulas, and it suggests a common generalization that should look like, well, maybe we should replace this HQ here by a convex combination of entropies, and we need some kind of quantity here which measures again the distance from these lambdas from the spectrum of each of the marginals at the same time. So we should look for a generalization of this form. 1 over 1 minus alpha is just a normalization that was not included. So this was included in this entropy, in this Rényi entropies, but not included in the previous table. So as I said, I take this 1 minus alpha times the convex combination of entropies minus alpha times some quantity which depends on psi and these lambdas. So what kind of function could this psi be? So if we want to get back the alpha equals 0 case, then when alpha goes to 0, then the actual value of this function is not relevant anymore, but in the limit alpha goes to 0, it will still remember whether this number was finite or infinite, as we saw with the Schmidt-Rank formula. So this should be a function that is infinite outside the entanglement polytope. And by looking at the other extreme case, when alpha is equal to 1, then the first term vanishes, and then we should get back the norm squared, so that gives the infimum of this I psi. For bipartite states, it must reduce to the Kullback-Leibler divergence between the order spectrum and the two arguments. So in that case, the entanglement polytope consists of pairs of probability distributions that are equal to each other. So that's why this equality is here. And there's also scaling property that's also required to get the right behavior in the end. And to actually find such a function, we should have a look at the spectrum estimation procedure given by the empirical Young diagram measurement, which goes as follows. So the problem here is to estimate the spectrum of an unknown density matrix. So we take n copies of this state, and we're allowed to perform some measurements on these n copies, a joint measurement, and output an estimate for the spectrum. And one proposal for doing this is to decompose the nth tensor power Hilbert space with respect to the unitary group and the symmetric group, which is also called a Schur-Wright decomposition. And this gives a bunch of projections. These lambdas are integer partitions of the integer n. So decreasing vectors of non-negative numbers summing to n. And these parameterized the isotypic components for this reduction, for this decomposition into irreducible. So these are irreducible representations of these groups. But in particular, we get a bunch of pairwise orthogonal projections which form a PVM, so projection valued measure, and the empirical Young diagram measurement uses these PVM elements as the measurement. And when we measure the projection corresponding to the partition lambda, the output is taken to be just a normalized partition. So we divide each entry by n, and then we get a non-increasing probability vector. And this will be the estimate for the spectrum. What Kyle and Vrana found is that these output distributions satisfy a large deviation principle, which roughly means that the probability of getting an estimate around lambda bar, so that's some point in the output space of non-increasingly ordered probability distributions, the probability of getting an estimate around this lambda bar would be exponentially low, with the exponent given by the relative entropy distance of lambda bar from the order spectrum of rho. What we need in this problem is a simultaneous version of this, or a local version of this empirical Young diagram measurement. In this case, the input is n copies of the k-partite state, and each of the parties have access to n copies of their own subsystem, so they can perform this empirical Young diagram measurement on their part. So like the first party has h1 tensor n, and then plays the same game as on the previous slide. So they do this decompositions locally and measurements locally, and they output k estimates for for the k marginals, for the spectra of these k marginals. So what happens is that, once again, the probability of obtaining an outcome around a certain collection of ordered probability distributions will decrease exponentially with a certain rate function. And what turns out is that this rate function is the right object that we will be using. So, for example, local observations will look the same as before. So that means if we take the infimum over all but one of these distributions, then we get the relative entropy distance from the respective marginal. But these observations will not be independent of each other. There are non-trivial correlations between what the parties see. And in particular, there's a very strong constraint that the estimate will always lie in the entanglement polytope. So that means that this rate function I is infinite outside the entanglement polytope. That's a property of this local empirical Young diagonal measurement. And let me mention here that in these two works, we obtained an explicit formula for this rate function, also in a more general setting, but in our case, this is what we get. So this kind of optimization tells us what the rate function is. So let's get back to the main result again. So let I psi be the rate function for this simultaneous empirical Young diagram measurement, and then define the quantities as on the first slide, but using this notation now. So we take the supremum of a convex combination of the entropies minus a term that penalizes everything that's not the collection of the marginal spectra of the state, and we are allowed to tune this parameter, this penalty parameter. And then we just take the supremum over all these marginal spectra, or estimates for marginal spectra. So these are non-increasingly ordered probability distributions. Then what we get is, after rescaling and exponentiating, what we get is an element of the asymptotic spectrum of LOCC transformations. So this F is multiplicative under the tensor product and additive under the direct sum, normalized on separable unit vectors to it takes the value 1, and it's non-increasing under trace non-increasing LOCC channels. So in particular, if we go back to the logarithmic version, that would be an additive entanglement monotone. So additive in the sense that its value on psi tensor phi will be equal to the sum of its values on psi and its value on phi. And in the certain limits, we recover the previously known elements in the spectrum, as I promised. So when alpha goes to 0, we get the SLOCC monotones introduced in an earlier paper. When theta is chosen to be an extremal point, so that means one of the thetas is equal to 1 and the other ones are 0, then what we get are the marginal Rayleigh entropies as alpha goes from 0 to 1. And finally, if alpha goes to 1, then, well, in the exponentiated form, we get the norm squared, but in this logarithmic form, because of this 1 over 1 minus alpha factor, we get a different thing. Namely, we get convex combinations of the marginal Shannon entropies of the state. And let me mention another characterization of the same quantity in terms of another quantity, which is a lower counterpart. So this will be something that's lower than what we had before, so lower bound. And this again given by an optimization problem. So this time we take the supremum over products of, say, cross operators. So these are like cross operators. They satisfy condition, like the kj star, kj must be at most 1. And we act with the product of these cross operators on the state psi. We normalize it and take the convex combination of its marginal entropies. So that's the first term. Whereas in the second term, we just take the norm of the result. So what we used here for normalizing that. We take the logarithm of that, again with a tunable parameter. And it turns out that if we take this quantity and regularize it, so we evaluate it on n copies of psi, divide by n, and let n goes to infinity, then we get the quantity that we had before. And this second characterization is useful for proving the supermultiplicativity and superadditivity, whereas the one that I had before is used for proving submultiplicativity and subadditivity. And it's interesting to know that at least when alpha goes to 0, so in the alpha equals 0 limit, and there's actually no need to regularize. So that's an earlier result that in that case we get the same thing by considering these two expressions. I don't know if this is the case when alpha is not equal to 0, but at least the regularized version of this quantity is equal to the previous one. So let me conclude. So what we have is a collection of entanglement measures that might be called the Rényi entanglement measures, interpolating between the asymptotic monotones and convex combinations of the normal von Neumann entanglement entropies, which give bounds on the trade-off curve for probabilistic entanglement transformations, and in the sense introduced in the beginning of the talk. Right, so recall that this E star is equal to the infimum over the asymptotic spectrum of a similar fraction. So since we have a bunch of points in the asymptotic spectrum, that gives an upper bound on the infimum. We take the infimum over a subset. So what's still missing is that I don't really know how to compute this quantities other than this formula that might not be too easy to evaluate. And this could mean numerical difficulties and also analytical difficulties. And another question is what happens if other bipartite cuts are considered. So in this case, we interpolate between this the Rényi entanglement entropies for special cuts of the system, for when we do a cut where we group together one party and the rest. But there are also other bipartite cuts, and the Rényi entanglement entropies are also in the spectrum across those cuts. So is there also a way to interpolate between all of them? Another interesting direction would be to look for constructions and particular instances of pairs of states where we have an equality here. So even though this subset might not be able to characterize the rate or the error exponent rates trade-off for all pairs of states, there might be specific pairs of states where it's actually sufficient to consider these quantities. And of course, we would like to understand the whole asymptotic spectrum. That's maybe the most pressing open questions in this problem. Thank you for your attention.